Okay, let's move on to FRQB from Unit 7, Progress Check, problem number 2. I'm given this diff EQ, and then part A actually just asks me to sketch the solution curve through the points 0, 1 and 0, 5 halves. And I am actually given my slope field right here, okay? So it's got this point 0, 1 and 0, 5 halves. Hopefully we can very easily see, I'm gonna pull out a pencil because I don't want to get permanent marking on this guy. But hopefully we can very easily see that the solution curve through 0, 1 is going to be this horizontal line y equals 1, right? I follow that path. And that should make sense. If I plug in y equals 1, no matter what value of x, this term is going to be 0, so everything else is going to go to 0. So that's my easy solution curve. Okay, my next solution curve is a little bit tougher. I go through this point, 0, 5 halves, but hopefully I can see, right? I'm gonna follow in between these lines at this point. It means that I'm turning around, kind of like there was, it's a curve. Totally lost my train of thought. But I'm turning around, right? Like a curve, okay? And then I'm gonna come on up and I'm gonna connect with this guy. And I'm going to continue connecting with this guy till I hit, what point is it? It's gonna be this guy right up here till I hit here. These slopes of 0, don't be fooled, right? This is a slope of 0, meaning at some point I'm gonna hit this point and turn back around, right? A slope of 0 means I have a relative min or a relative max, okay? This, while it kind of looks like maybe I have a horizontal asymptote, I would have a slope of undefined right here. But this is a slope of 0, meaning I am going to hit that curve and turn around. And I'm going to turn back around and follow this guy. It gets quite steep and come through here, okay? So I've got that. Now I can follow this guy. This guy's a little bit easier, right? I can follow this curve and I see that, what's going to end up happening? Well, I'm going to go, I went 1, 2, and I believe I'm going to do something like this, okay? There is my solution curve right here. So I've got this guy and that guy. And my rubric, right? I get 1 point for having the correct curve through 0, 5 halves and 1 point for having that horizontal line through 0, 1. So 2 points total, right? Okay, let's move on. Let's do part B. Part B asks me to write an equation, right? Write equation. Hopefully this is coming familiar to you, of the line tangent to the curve through the point 0, 5 halves. Tangent to curve through that point, okay? So again, it means I'm using this formula, y minus y naught is going to equal m times x minus x naught. My x naught is 0, my y naught is 5 halves, and my slope m is going to be dy dx at that point, 0, 5 halves. So let's see, at that point, 0, 5 halves, I have 5 halves minus 1 times 0 plus 1 times the cosine of 0 squared plus 2 times 0 plus pi. Ooh, barely had enough room there. So 5 halves minus 2 halves is going to be 3 halves times 1 times the cosine of pi. So this is going to be 3 halves times -1, so it's going to be a -3 halves. So pulling it all together, it means that y minus 5 halves is going to equal a -3 halves x. right? It would be x minus 0. So this guy right here is my answer, and ooh, fortunately I only get 1 point for doing that correctly. That is it. All right, so most of my points then go to this bad boy, the last part, C. And it actually asks me to find my particular solution, y equals f of x, and it is going to be with the initial condition f of 0 equals 5/2. So I've got dy dx, which equals y minus 1 times x plus 1 times the cosine of x squared plus 2x plus pi. I've got my diff-EQ. I'm going to separate my variables and integrate it. So I'm going to put my y's together and keep my x's together, which means that dy all over y minus 1 is going to equal x plus 1 times cosine of x squared plus 2x plus pi times dx. So let's integrate these guys. The integral of dy all over y minus 1 is going to equal the integral of x plus 1 times cosine of x squared plus 2x plus pi dx. This guy's a really simple U substitution. I'm going to show you my U sub work, but like the question that was asked earlier today, ooh, you're probably not going to see this until Saturday, but I'm doing this on Thursday. So it was asked during our Zoom session about, do you need to show all your work for this U substitution? No, because this one is simple enough. Now this guy, you should probably show your work for this U substitution. I'm going to show both. So if I let u equal y minus 1, du is going to equal dy. So this very nice and easily becomes the integral of 1 over u du, which is going to be ln of the absolute value of u, which becomes ln of the absolute value of y minus 1. This guy's a little trickier. I'm going to let u equal what's inside of cosine. X squared plus 2x plus pi, which means that my du is going to be 2x plus 2 all times dx, right? I'm taking the derivative with respect to x, so I'm going to have a 2x dx plus a 2 dx, so I'm just factoring that out, which can also be rewritten as 2 times the quantity of x plus 1 dx. And now hopefully this is clicking for you guys and you are seeing that, oh, I have an x plus 1 and a dx in my original problem. So I need to just simply divide by 2 so that I can replace my x plus 1 dx with du over 2, and then this becomes cosine of u. So my integral becomes 1/2 times cosine of u du, which is, right, 1/2 times sine of u, and I'm putting the c over here. So finally, let's see, this is 1/2 sine of x squared plus 2x plus pi plus c. So finally I can pull it all together. It means that the ln of the absolute value of y minus 1 is going to equal 1/2 times the sine of x squared plus 2x plus pi plus c. All right. Now in this circumstance, I think I'm going to solve for c right now. Yeah, let's go ahead and do that. I know that f of 0 is 5/2. So when x is 0, y is 5/2. So I've got the ln of 5/2 minus 1. I dropped the absolute value because 5/2 is greater than 1, so this will be a positive number. Is going to equal 1/2 times the sine of 0 squared plus 2 times 0 plus pi plus c. So what, 5/2 minus 2/2 is going to be 3/2. So the ln of 3/2 is going to equal 1/2 times sine of pi plus c. Sine of pi is 0, so that's going to be 0 plus c, which means that c equals the ln of 3/2. So let's plug that in. That means the ln of the absolute value of y minus 1 is going to equal 1/2 times the sine of x squared plus 2x plus pi plus the ln of 3/2. And in order to get rid of the ln, right, I need to raise it to the e power. So e to the ln of the absolute value of y minus 1 is going to equal e to the 1/2 sine of x squared plus 2x plus pi. I'm going to skip this step right here, right? It would be plus, okay, fine, I won't skip that step. Plus ln of 3/2, which can be rewritten as e to the 1/2 sine of x squared plus 2x plus pi times e to the ln of 3/2. Right? That's how I can rewrite these guys. And hopefully I know that this is 3/2, right? E to the ln of 3/2 is 3/2. So I'm going to move on to the next page. Actually, I'm going to go on to the back side to continue this problem. So I had, right, e to the ln of absolute value of y minus 1, which means I'm left with absolute value of y minus 1 equals 3/2 times e to the 1/2 sine of, what was it, x squared plus 2x plus pi. Okay, that's where I'm at. And then again, this means y minus 1 can equal the positive version, sine of x squared plus 2x plus pi, or it could equal the negative version, right? Y minus 1 can equal negative 3/2 e to the sine of x squared plus 2x plus pi. Let's work through the positive version. This means that y equals 1 plus 3/2 e to the 1/2 sine of x squared plus 2x plus pi. Does the positive version satisfy that y sub 0 equals 5/2? Does it satisfy that? Well, y sub 0 is going to be 1 plus 3/2 times e to the, well, 0 means I've got sine of pi, which is 0. So it's going to be e to the 0. So that's 1 plus 3/2, which equals 5/2. Awesome. So I don't need to move forward to solve for that negative version because I see that my positive version satisfies my initial condition. Okay? If this guy didn't work out, then I do need to move to that negative version. Okay? All right, so let's take a look at that rubric. This guy is worth 6 points. All right, that is a lot. Okay? Oh, did I even show you the rubric for? No, I don't think I showed you the rubric for part B. I just said it was worth 1 point. And your 1 point is for properly getting the equation of the line tangent. Sorry. Okay, part C. Again, hopefully it's ingrained in our memories by now that if I do not separate the variables, I will get 0 points. Okay? And then if I do not have a constant of integration, this guy's a little bit more generous. I can still get 4 out of 6 points, but sometimes it's a lot less, okay? And then my 6 point has an expression for y. So let's see what they give me my points for. I get 1 point for properly separating the variables, 1 point for doing the proper dy antiderivative. Now notice here, right? I get a point for using a u substitution with dx. They don't specify right here that it's with dx, but it is with dx because dx has a little more complex u substitution. I get a point for having the proper antiderivative, a point for getting the constant of integration by using the initial condition, and for my answer. So there's 1 point right here. Let's go back to the rest of my work. Okay, I got a point for separating the variables right here. I get a point for getting the proper antiderivative for y. I get a point for using u substitution with x. And then I get a point for having the proper antiderivative here. And then finally, I get a point for having my constant of integration and solving for it correctly with my initial condition. All right, so I'm going to post the work here with the videos as well, but hopefully that helps you see. Oh, and here's all the work that they have as well. Notice that they didn't do anything fancy, right? They didn't say that this is the sine of this guy squared or the square root of that guy, okay? Yeah, we're not doing anything fancy. We can leave it how it is. Cool. Actually, I think that only works with logs anyways. Never mind. Ignore what I just talked about. Cool, cool. All right. Toodles, guys.